Hey everyone, and welcome. Today, we're going to dive into a force that, basically powers our entire world, but is completely invisible: the electric field. You've felt its effects your whole life, and we're about to see how it's kind of like the secret twin of a force we all know really, really well: gravity.
It's a fantastic question, right? I mean, gravity pulling an apple down just feels normal, obvious. But that weird static cling when you pull clothes out of the dryer, or that little zap you get from a doorknob, or, a balloon just defying gravity to stick to a wall. Well, that is the star of our show today. Its name is the electric field.
Okay, so to really get how all this works, we first have to define the playing field itself. We need to kind of map out this invisible influence before we can really talk about what it does.
At its absolute core, an electric field is just a region of influence. It's that simple. Just like the Earth creates a gravitational field that pulls stuff towards it, a charged object creates an electric field that can push or pull other charged objects that wander into its space. It's like this invisible web of force that fills the space all around a charge. Now, the source of this field, the thing that's actually creating it, is what we call a point charge. You can think of it like the sun in our little electrical solar system. It's the object generating this whole area of influence, and it can be either positive or negative. So, if the point charge is our sun, how do we see its invisible effects? Well, we use a planet, right? Or, in our case, something we call a test charge. And just by agreement, scientists decided it's always a tiny positive charge. We basically just place it inside the field and watch what happens. Which way does it get pushed? How hard? It's our little probe for exploring this invisible world.
All right, so we've met the main characters. But how do we actually visualize a field we can't even see? Well, we can't see it with our eyes, but we can definitely draw a map of it.
So these maps are made of what we call field lines, and they follow a few really simple rules. The arrows you see on the lines, they just show which way our little positive test charge would get pushed. The lines always flow away from positive charges and suck in towards negative ones. And here's the real kicker. Where the lines are all bunched up close together, the field is super strong, and where they're spread way out, it's pretty weak.
And here's exactly what that looks like in the simplest cases. On the left, you've got a positive point charge. It acts like a sprinkler, just pushing our test charge straight outwards in every direction. And on the right, you've got a negative charge. It acts like a drain, pulling our little positive test charge straight inwards from all directions. Simple, right? But also really elegant.
This is where it gets really cool, though. When you bring charges together, they don't just have their own separate fields, they interact. Their fields merge. Here, you can see the lines flowing beautifully from the positive charge over to the negative one, creating this amazing, complex pattern of force in the space between them.
So we've looked at the static map, like a snapshot in time. But what happens when we actually let a charge loose inside one of these fields? What's its journey actually like?
To study motion, physicists love to create a really simple, clean environment. And this is it, a uniform electric field. You can make one between two parallel charged plates. See how those field lines are perfectly parallel and evenly spaced? That means the force is the exact same no matter where a charge is inside that field. It's perfectly consistent.
So what happens when we drop a charge in there? It kicks off this beautiful chain reaction. The constant field creates a constant force. And what did Newton teach us? A constant force creates a constant acceleration, just like an apple falling near Earth's surface. And what that means is our charge picks up speed at a perfectly steady, predictable rate. And all that work the field is doing by pushing the charge along, well, that energy doesn't just disappear. It gets converted, one-to-one, directly into kinetic energy, the energy of motion. As you can see here, the farther the charge travels, the more energy the field pumps into it, making it go faster and faster in this perfectly straight-line, predictable way.
And this whole idea of energy brings us to a much deeper connection. We've been talking about the field as a force, a push, but you can also think of it as a landscape of stored energy.
This is something called electric potential. And honestly, the absolute easiest way to think about it is just electrical height. If you lift a bowling ball off the floor, you give it gravitational potential energy. It's the same idea. If you push a charge against an electric field, you're giving it electric potential energy. It's just stored energy waiting to be let go. And this is where it all just clicks together so perfectly. The electric field, the force itself, is just the steepness of that electric potential hill. A really strong field is like a super steep cliff where the potential energy just plummets and a charge you put there is going to accelerate like a rocket.
So the big takeaway here is super simple. A strong field
means you've got a steep potential hill, and a charge is going to move fast. A weak field, that's more like a gentle rolling slope, where the energy changes much more gradually. The force is literally just the slope of the energy landscape.
Which brings us full circle, right back to where we started, back to gravity. It's kind of crazy, but these two forces, one that holds galaxies together and one that holds atoms together, they follow almost the exact same rulebook.
So check this out. Both fields follow what's called an inverse square law. It sounds fancy, but all it means is that if you double your distance from the source, the force gets 4 times weaker. It's this fundamental rule for both of them. But here's the massive game-changing difference. Gravity only pulls. The electric field can push and pull. It can attract and repel.
And you see the exact same story with their potentials, with their energy landscapes. The math looks almost identical. So the real punchline is that this one little difference, the fact that there are positive and negative charges, changes absolutely everything. It allows for repulsion, it allows for things to cancel out, and it allows for the incredibly complex chemistry that makes our world and us possible.
And that leaves us with one last big idea to chew on. Gravity, since it only ever pulls, is great at clumping matter together into planets and stars. But the electric force, with its amazing ability to both push and pull, creates this delicate dance, this incredible balance that builds molecules and life and all the intricate structures we see around us. So how does that constant dance of attraction and repulsion truly shape our universe? That's a question worth thinking about.